Vado, okay? Good morning, everybody. Welcome to the first plenary talk of today. And I have the honor to introduce our speaker, who is Camilo de Lellis. I had to write a cheat sheet because there's too many things I have to say about his career. So I hope you don't mind if I read something here. So he's originally from Italy, from San Benedetto del Tronto. And he studied at the Scuola Normale Superiore in Pisa under the supervision of Luigi Ambrosio. He was a postdoc at Max Planck in Leipzig and at ETH in Zurich. He then was a professor at the University of Zurich. And then in 2018, he was hired by the Institute for Advanced Studies in Princeton. As far as research, he is one of the members of this renowned Italian school. He's a specialist and gave fundamental contributions to geometric measure theory, theory of PDEs in general, hyperbolic systems of conservation laws, and fluid dynamics. He is one of the managing editors of the journal Inventiones Mathematicae. Along his career, so far, he has supervised around 20 PhD students. The list of prizes and awards that he was awarded is very impressive. So let me give you just a very quick list. 2009 Stampacchia Medal, 2013 Fermat Prize, 2014 Caciopoli Prize, 2015 Amerio Prize, 2020 Bochner Memorial Prize, and 2022 Mariam Mirzakhani Prize. That's very impressive. He was a plenary speaker at the last ICM in 2022, officially in St. Petersburg, but you know. And then he also got another award, which is an invitation to be a plenary speaker of the 34th Brazilian Colloquium of Mathematics. And so I am very honored to introduce Professor Camilo de Lellis.
Yeah, my voice is very loud, but still. Thank you very much. So it's a great pleasure to be here. It's also somewhat humbling given the history of IMPA in minimum surfaces. In fact, the first time, so in the very first year of my undergraduate studies that I did in Pisa, the people in Scuola Normale had this idea that they wanted to experiment and kind of bring us, in the first year of undergraduate, from no knowledge of calculus till the Theorema Egregium of Gauss in 1 year. So we received a crash course in one variable and multivariable calculus, which, you know, the English crash course is very appropriate in this case. It was not a soft landing. And then at the end, one of the mathematicians there took over. So it was done by a few people. So first variable calculus by one person, second multivariable calculus by another person, and then the last mathematician actually started with differential geometry. And you know, let me put it this way: he wasn't the clearest person in explaining things, and it was very complicated. And we were like, you know, all of us kind of lost on these concepts until one of us actually said, well, you know, I heard there is this wonderful book called Do Carmo. And then we opened Do Carmo, and actually, we started understanding everything. The book was simply marvelous. And it's also the first time that I actually encountered this notion, the notion of a minima surface, which in the book I'm referring to is actually the one on curves and surfaces, which, I mean, all of the books of Do Carmo actually are absolutely fantastic. But, you know, that one was kind of fundamental for me. And it's the first time that I actually saw minima surfaces. So let me go into a little bit of the history of the problem. So this is what is called Plateau's problem. So you're given a one-dimensional contour gamma in the three-dimensional space, and you want to find the surface sigma of least area which spans it. And this is the Belgian physicist Joseph Plateau, who lived in the 19th century, and he was actually interested in this problem because he proposed it to model the shape of soap films. Okay? So the idea is that we take a wire. So the wire is actually the one-dimensional kind of frame, the boundary of this surface sigma that we want to find. We dip it in soapy water, and then we take it out. Okay? It builds very interesting, very beautiful shapes. And the shapes that come out, according to Plateau, they are minimum surfaces. So surfaces that try to minimize the area among all surfaces which span the same contour. Okay? So, but in fact, as it happens pretty much everywhere in mathematics, the attribution is not correct. So the first person to actually consider in the mathematical literature, but also in the physics literature as far as I know, minimum surfaces, is Lagrange in 1760. Okay, so it's in this paper, which, you know, appears in Miscellanea Taurinensia in 1760. So, in fact, Lagrange, born as Giuseppe Luigi Lagrangia in Torino in 1736, where he lived till 1766, so that paper was written in Torino. Then he moved actually to Berlin and then finally to Paris in 1786. So what is he doing actually in this paper? Well, in this paper, he actually establishes his theory on how to find necessary conditions for minima of integral functionals in the calculus of variations. So that is where he famously derives Euler-Lagrange equations, what we call today Euler-Lagrange equations. And in kind of pretty much all the work is actually interested in one-dimensional problems. So he's dealing with integral functionals which depend on a function of one variable. And in particular, one thing on which he insists is the derivation of the Brachis-Stockron, which was already a problem which was solved by Bernoulli previously, but now he solves it with his own powerful method. Okay, and then he writes an appendix. I'm fond of writing appendices, especially after, you know, I see histories like this. So he writes in the appendix, and in the appendix he says, well, you know, I've given you the theory of one-dimensional kind of integrals, but my theory is extremely powerful in principle. There's no reason why I should actually confine to that. I can actually look at minimum problems, not only among curves, but also among surfaces. For instance, maybe you're interested in finding the surface of least area which spans a given contour. And here's the appendix, right? So you see, right? And I mean, you see, I mean, instead of, you know, I can even look for maxima and minima of curved surfaces which, you know, want to minimize or maximize a certain integral function, okay? And so here is where he writes actually the integral functional. So you see over here is dx dy square root of 1 plus p squared plus q squared. So what is p and q? P and q are the partial derivatives of the function in direction x and y. And see, he's using x, y, and z. So x and y are the independent variables, and z is actually the function itself, right? And it's very nice because, well, here is the derivation of, you know, the other Lagrange equation in his words is actually using differential forms. And, you know, on the next page he says, well, the problem is in fact reduced to finding p and q which satisfy the following conditions. So this differential form and this differential form must be complete differentials, which in his language means actually they have to be, in our language, exact differentials. So I'm going to write it for you again here. So he derives the minima surface equation, even though he doesn't write what we call nowadays a partial differential equation, which is what we would do. He just says, I have these two differential forms, p dx plus q dy, and q dx minus p dy divided by square root of 1 plus p squared plus q squared, okay? And they have to be exact differentials. And of course, if the first one is an exact differential, then you have p equal du dx and q equal du dy. And if the second is an exact differential, then it has to be a closed form, right? Of course, a closed form is a necessary condition, and on a simply connected domain, it's also a sufficient condition. Now, if you write down what it means for this form to be closed, once you know that p and q are actually the differentials of the functions, voila, you find this equation over here. Divergence of gradient of u divided by square root of 1 plus modulus of gradient u squared is equal to 0. So that's the minima surface equation for a function of one variable, which is a critical point of, written in this form, actually you could do it in every dimension, but so this is for hypersurfaces. So this is a graph so an hypersurface, which is a graph of a function u, which is a critical point for the area function in modern terms. Well, that's what you find, for instance, in Carmo when he writes down the equation. OK, so it's kind of remarkable that it seems to be the first elliptic partial differential equation ever written, as far as I know. I mean, I'm not an historian, so I might actually be saying something wrong. But for sure, it appears way earlier than its linearization, which is the Laplace equation, Laplacian of u equals 0, which, you see, if I take the divergence of the gradient of u and I ignore kind of the denominator, then I have Laplacian of u equals 0. And, you know, if the gradient is very small, then essentially this one, if you were a physicist, you would ignore, and you would say, well, you know, approximately is the solution of a Laplace equation, which, I mean, if you want in mathematical terms, if you make a Taylor expansion of your PDE, the Laplace equation is the linearization of the minima surface equation around the point where the tangent is flat, okay? And the Laplace equation is the linear equation, actually is written afterwards. So quite remarkable. OK, let me go back to the plateau problem, which is really the focus of my talk. So here is a very general version of it, right? So I take now not only a surface gamma, which is a one-dimensional curve, but I just take an m-1 dimensional surface. And I can do it in a Euclidean space of any dimension, but in particular, I can even just put myself in a Riemannian manifold, right? So where I have a concept of length, and therefore I have a concept of volume, okay? And of surface area. So now I'm in this ambient manifold M, and what I want to do is I want to find the m-dimensional surface sigma, which bounds gamma and has least volume. I keep saying the m-dimensional surface, but actually there are many examples in which the minimizer is more than one, because this is not, in general, a convex problem. So uniqueness of the minimizer is false, okay? Now, the first question that you want to ask is, though, you know, what should we understand? As surface, as bounds, as volume? We could just like limit ourselves at discussing only surfaces which are smooth, for which I have the formula for computing the volume. And then the concept of bounds must be, I don't know, something like which we take from differential topology. That's good, but there are many answers to this question if you want to like look for surfaces which are not completely smooth. Maybe with surfaces which have, I don't know, edges or, and you might actually challenge that. Why should I do it? Well, for instance, because when we took like, you know, this example with soap films in my pictures some time ago, you might have noticed, if you were paying attention, that not all of them are actually smooth everywhere, right? I mean, some of them were smooth, but some other were actually making edges. If I really go much back, see, you see some of them are actually making edges, right? So you see, for instance, this guy or that guy. Well, OK, it's not so clear. I should have actually taken a much bigger picture. Anyway, so they're not necessarily smooth even in the physical world if you're really looking at the original problem of Plateau. So now here's one classical answer. This actually dates to 1930, and Jesse Douglas got the Fields Medal for this answer, one of the first two Fields Medals, together with Alfors, I think. So one possible way to actually define all of these concepts is just to say, well, let me fix an abstract manifold sigma prime, and I just look at all maps phi, which map sigma prime into M, such that when I restrict phi to the boundary of this abstract manifold, I have an homeomorphism onto gamma, okay? And then I have a formula for computing the area. And this map phi doesn't need to be necessarily smooth. I mean, if it is C1, if it has one derivative and it is differentiable, it's the usual formula. But, you know, he takes less smooth functions phi. And I mean, both Douglas and Rado build an existence theory for two-dimensional surfaces in general ambient manifolds, okay, using this idea. But it's kind of, you know, forced in a sense because you have to fix this abstract manifold, which means you're fixing the topology of the surface. But what do you know about the topology? I mean, why should it be, for instance, a disk? Or why should it be, like, you know, a surface of genus 1 or genus 2 or whatever? Maybe you want to do something which is more general. So when you wanted to do something which is more general, you start think actually, oh, there's a typo over there. Okay, so that is not, so what that is intended to be is geometric measure theory. So you start entering into a subject which is called geometric measure theory. So geometric measure theory exactly asks, among many other questions, the question of what is, like in general, a good concept of m-dimensional volume, what is a good generalization of the concept of surfaces, what is a good generalization of bounding a given contour, okay? So these are like pivotal questions in geometric measure theory, which is a rather kind of new subject. So it was born actually in the 20th century, essentially at, between the First and the Second World War, right? With foundational papers by Hausdorff, Bezikovich, and a few other people. Okay, so they're kind of, I like to bundle, because there's many answers to the questions that I posed. I like to bundle them into two big families. One of them I call set theoretic, and one pioneer of that was Reifenberg in 1960. So in the set theoretic method, you do the following. So you say, well, what is your surface? Well, my surface is any set, sigma. Maybe reasonable, maybe with some measurability assumption. It's any set, but then I have to tell you what is the volume of the set, and there's a good definition for that in general. It's called Hausdorff measure, and you study it in basic courses in measure theory sometimes, if the person who's actually teaching measure theory is going into more advanced stuff. And the good thing of Hausdorff measure is that it coincides with the usual volume if the surface is smooth, right? So you want something like that as a property. And you have to say what it means to bound that sigma bounds gamma. Well, there topology enters. So one way to say that sigma bounds gamma is to say that gamma is trivial in some topological sense inside your surface sigma. For instance, Reifenberg proposes Chesh homology, okay? But, you might give other proposals. Okay, and then here you have your setup, and now you want to minimize among all possible choices. Okay, so that's one way. There's another thing, which I could call the functional analytic way, but it's somehow the Italian way. So actually, it's quite interesting because at the beginning of, at the birth of geometric measure theory, there was a sort of a competition between different groups, and Calciopoli was kind of an isolated figure in Italy. And he was saying to the rest of the world, essentially, what you guys are doing is actually not really what you should be doing. He was a very assertive person. Then he got actually very bad math reviews, probably as a consequence of this. Anyway, he said, well, what you should really do is, first of all, you fix a class of surfaces that you like, okay? Do you like smooth surfaces? Fine. Then, fix all the class of smooth surfaces. And you start with that. That is your basic model that you want to use. Then you should, for instance, like, in the case of De Giorgi, which then kind of is really implemented. So Calciopoli kind of gave this idea, but didn't do anything with it, essentially. So De Giorgi was the first one to really implement it effectively, to build an existence theory, which was very appealing. So you fix a class of desired sigma, for which you know what is the concept of boundary, and for which you know what is the concept of volume. For instance, because they're nice objects. Okay, then you decide the topology on it. Good, and I will tell you what we mean by good. Now, once you decide the topology, you complete the space. So your generalized surfaces should not just be like something that you cook up, any set in Rn, but should really be something which is in the closure of the objects that you wanted at the beginning, right? So, and now, once you complete the space, you actually extend the volume as a lower semi-continuous function, and you extend the boundary possibly as a continuous map, okay? And if you're able to do that, good means that you can actually apply the direct methods of the calculus of variations. And by applying the direct method of the calculus of variations, what you would hope to do with this theory is that you take a minimizing sequence. This minimizing sequence is converging somewhere because you have some compactness in this space. And then because you have lower semi-continuity of the volume, that guy is going to be actually an actual minimizer, okay? That's what you want to do. And this is actually what can be done in big generality with the so-called Federer and Fleming theory for the oriented plateau problem. That's what I'm going to present. And in the case of codimension 1, this was actually predated by this work of De Giorgi that I said. So this one is a kind of like, generalization which works in any dimension and codimension, whereas De Giorgi's theory was really good for hypersurfaces. Okay? So you start with the usual singular chains with coefficients in some normed group. What I actually now want to do is I want to use the integer as a normed group. Okay, and what is a singular chain? It's nothing scary. It's just the formal sum of images of simplices through a smooth map, right? So it's what you really would use in homology theory. So you have, in 2D, distorted triangles. So you start with triangles, you kind of map them into your space through a map. You take many of them, and then you attribute multiplicities to them, which are integer, and then you take a formal sum. That's your space of surfaces. Now, the boundary is the usual operation, and the volume is the usual volume, because all these objects are actually smooth. But you have to be a little bit careful, right? So because the sigma i's might overlap, right? If there is no overlapping, then the volume is just the sum of the volume of the volumes, and of course the multiplicity is giving you, with the moduli, something in front. Okay, what is the topology? So now this is a little bit more complicated. So I'm going to give you a model for the topology. So if you take sigma 1 and sigma 2, which are two chains with equal boundary, the difference between them, they are the boundary of something, lambda. And what you want to do is you want to sort of minimize the volume of lambda over all possible things. So let me give you like a picture over here. So if the two guys span the same boundary, so you have something like this, okay, then there's a two-dimensional surface over here if these were like one-dimensional objects, which kind of closes it, at least in the Euclidean space. And then among all membranes, you try to find kind of the infimum, and that is kind of the distance between your two curves, right? So if they don't have the same boundary, there's something that you can do is to add some portions and then close your space. And then you compute how much length you have to add and how much area you have to put to fill things, okay? And you infimize, and you have a concept of a distance. So very good. So now once you actually put this topology, the completion is the space of so-called flat chains. And a subset of that is what Federer and Fleming use actually for the plateaus problem. It's the subspace of integral currents. So and the reason why this is a good subset is because the boundary of your problem is fixed in plateaus problems. So that's why you can sort of dispense and go into a smaller space. So now, what are integral currents? So they have a particular structure. So remember that your space of flat chains was this, let me use this, was this finite sum. And remember that there are integral coefficients, and then there are kind of building blocks, which are images of simplices. So now, instead of having a finite sum, you have an infinite sum. So you have a countable collection. Now, instead of having simplices, you have subsets ki of C1-oriented surfaces gamma I of the correct dimension. So instead of having these nice distorted triangles, you might have kind of Swiss cheese inside subsets type, okay? Because you're just taking general closed set inside. And then you have positive integers. And now instead of taking the formal sum, you take a series. But to be an integer rectifiable current, under the stipulation that these sets are pairwise disjoint, which you can actually reach with a simple trick, at least in leaving aside a set of measure 0, there is one further stipulation, which is some sort of convergence of the series. So here, I mean, ki, I told you they are positive integers. And the reason why I take positive integers is because if I have a negative integer, what I would just do is I would flip the orientation of my surface gamma I. So by up to flipping the orientation of the surface gamma I can actually stipulate that ki is positive. And then I want a convergence of the volumes, right, times the corresponding weight. And the reason why I want to do that is because you imagine this is going to be my concept of total mass of my integral current. Okay, now, this is what Federer and Fleming call an integral rectifiable. So I have replaced a formal sum with a formal series, which has some convergence property. And I have replaced the simplices with possibly more complicated objects, which are sitting inside nice surfaces, but they can be very general. So you start seeing that it's some sort of like, Lebesgue theory, if you want, Lebesgue set theory for surfaces rather than the top dimensional situation. So now, an integral current is a current for which both the current itself and the boundary of the current are integral rectifiable, okay? And I mean, if you're interested in the plateau problem, the boundary of the current is fixed. And you probably fixed a priori something which is kind of a smooth boundary. So that assumption is for free. So when you're interested in the plateau problem, that assumption is really on what you're using to fill the curve, okay? So now one of the big theorems of the Federer and Fleming theory is that in this space, a solution of the plateau's problem can always be found through the direct methods of the calculus of variation. So you have enough compactness to take a minimizing sequence and say that it converges somewhere inside your space. You have lower semi-continuity of the volume to say that the final guy is actually a minimizer. So the limit of the volumina on the sequence is actually converging to the final volume then, as a consequence. So that's very good. But of course you could ask, well, do I know it? I mean, do I really need it? I mean, maybe to start with, I always have nice, smooth minimizers. And so I could do without this idea that I have to complete the space. So in retrospect, say, for instance, that you're at the beginning of the 20th century, and you're wondering about harmonic functions. Yeah, sure, harmonic functions are the minimum of the integral of gradient of u squared. Now you're doing all your Sobolev theory. You introduce W12, H1 to just say that you can apply the direct methods of the calculus of variation. But in the end, you find an harmonic function which is really analytic. So in a sense, it looks like a joke at the beginning, right? So your colleague can come nearby and say, well, you're looking for the harmonic function. Here, I give you the formula with potential theory, for instance. It's a good point of view. Nonetheless, we do study Sobolev functions anyway. And they actually were born that way. But anyhow, in this case, actually, we do need them because area minimizers can be singular. So these are two very famous examples. So this is a theorem by Bombieri, De Giorgi, and Giusti in 1970. I forgot to put actually the date. So take this sigma. So this sigma in R8 is just an explicit algebraic surface, which is nothing but the cone on the product of two three-dimensional spheres. That's just the exact formula for it. It's obviously singular at the origin, right? This guy, which is called the Simon's cone, is actually an absolute minimizer if you cut, say, the surface with a sphere of radius 1. So you cut the surface with a sphere of radius 1. You have a super smooth object, which is the product of two three-dimensional spheres. And if you try to fill it inside with anything which is smooth, you're going to have strictly more area than that minimizer over there. On the other hand, there's a simple way of smoothing the singularity. So you do get a sequence of smooth surfaces which bound your nice S3 times S3, whose volume is converging to the volume of this minimizer. So if you try to minimize among the space of smooth surfaces, there's no way you're actually getting a smooth minimizer. A smooth minimizer for this boundary does not exist. And you do catch this example with the theory of Federer and Fleming, as I told you. Now, here's another theorem. So this is a theorem by Federer around the same times as the theorem of Bombieri, De Giorgi, and Giusti, but it's based on a previous differential geometric computation of Wirtinger in complex differential geometry. So now consider this thing. So you take in C2, which I identify with R4, an algebraic surface again, which satisfies, so Z1 and Z2 are the two components of the vector Z, and it satisfies this equation over here, okay? So now this one, again, is a very nice surface, two-dimensional surface outside of the singularity, but it's not smooth in 0, okay? So there's a singularity in there. Now again, if you cut it with a one-dimensional sphere in your four-dimensional space, you actually find a real analytic curve. It couldn't be better than that. But again, you have the same phenomenon. Anytime that you try to fill this curve with something smooth, you find something which has area which is strictly larger than this guy. On the other hand, you can smooth the singularity and find a sequence of surfaces which bound your real analytic curve, whose two-dimensional area is converging to the two-dimensional area of the minimizer. So this is a needed singularity for the plateau problem, for the oriented plateau problem. And it's also something that you capture with this theory of integral currents, okay? But that you wouldn't capture if you just insist on only having smooth objects. So that's nice. And in fact, Federer's theorem is much more general. Actually, it tells you that every complex k-dimensional subvariety of a Kähler manifold, so think about the n-dimensional complex space and think about an algebraic object inside, so like, 0 of algebraic equations or 0 of holomorphic equations if you want. So that object is always an area minimizing, so an absolute minimum of the area functional in this theory of integral currents, okay? So what I showed you is just a simple example of an algebraic curve in C2, a one-dimensional, one complex dimensional object, but it's true in the uttermost generality. And now, one thing that you have to understand here is that I say it induces an area minimizing integral current. I have to choose an orientation for my subvariety, but there's something very nice that these complex subspaces have a very natural orientation, because there is the action of the imaginary unit, and that is how you actually orient in a kind of canonical way any k-dimensional complex subvariety of a Kähler manifold. Okay, so this is an example which is even more complicated than before, right? So I'm just like, I'm going to use this example later on for some purposes, okay? So this is just a more complex, more complicated complex curve. Okay, so now once you actually know this, there are two very natural, there's some very natural questions, right? So, okay, sure, there is a singularity, but, where and when is an area minimizer actually regular away from its boundary? So, in particular, one question that you can ask is, you have examples of singularities, but how large can they be? Can they be really many? Maybe, I don't know, there can be only a few. And once you actually ask how large is the set of interior singular points, you can also ask, okay, how do the singularities look like? So we saw two models. Maybe there's a theorem which classifies all possible models and tells you, like, in the neighborhood of a singularity, what is your surface going to look like, okay? So that would be a dream theorem that we're actually kind of light years, parsecs far from having. Anyway, all of these questions can be posed at the boundary points too, because you have a boundary. So even there you can ask, how regular does your surface attach to the boundary? But I'm not going to touch upon this argument. This would be actually material for another lecture. Okay, so here is a wonderful theorem which was reached in the 70s and the 80s. So take an m-dimensional area minimizing integral current. So this object that we got from the Federer and Fleming theory. And you are, in some m plus n dimensional Riemannian manifold. And this m is a smooth Riemannian manifold, even though I forgot to state it. Now, the set of interior singularities has a dimension bound from the theory, which is the following. So the dimension of the surface is m of the hypersurface if you are in n equal 1. So this is what you would call maybe hypercurrents. And then the dimension of the singularity is at most m minus 7. And this is through the work of several people in the 70s. De Giorgi, and I will tell you what De Giorgi did at the beginning, and then Fleming, Almgren, Simons, and Federer. In higher codimension, the situation is that you can actually have singularities up to dimension m minus 2. And this is the work of a single person, Almgren, in 1980. And that's a very famous work because of its hardness. So he actually wrote it on a typewriter because there was no LaTeX at the time. And the original manuscript was split into 3 volumes, which altogether made 1,728 typewritten pages. A hell of a lot of work. So now you see, it matches the example, right? So you remember we had the cone over S3 times S3 with an isolated singularity. So S3 times S3 is a 6-dimensional manifold. The cone is a 7-dimensional manifold. It was an hypersurface, and it had an isolated singularity. So 7 minus 7 equals 0. It matches the example. And M minus 2 matches the example too. We had a 2-dimensional surface in R4 with a point singularity. So 2 minus 2 equals 0. Now, you can build easily higher dimensional examples by simply multiplying your surface by a line, because there's a theorem by Federer which tells you that if you are in the Euclidean space and you have a certain area minimizing current, if you multiply this area minimizing current by a linear subspace, you get in higher dimension another area minimizing current. And of course, your singularity gets simply multiplied by this linear subspace. Okay? So, well, it seems you've done in some sense, right? So you have really a dimension bound which matches the singularities. Okay, but this doesn't answer the second question. That is, can we say more, a little bit about the structure of the singularities? And, a Hausdorff dimension bound is a very poor proxy for our notion of a set with the same dimension. So for instance, if I tell you that a set has a 0-dimensional Hausdorff dimension, so if I tell you that the set has 0 Hausdorff dimension, that set could be uncountable. Whereas when we think about the 0-dimensional set, we think about maybe finitely many points. So it's still kind of a very rough picture. So here's another theorem. And in fact, in the case of hypersurfaces, it was already in Federer's. So I could have stated in the case of M equals 7 and N equal 1, so hypersurfaces, which are area minimizer, oriented area minimizers of codimension 1 and of dimension 7, so the singular set is really discrete. It's a bunch of isolated points. It's much better than a dimension bound. It becomes a dimension bound only when you go to M bigger than 7. Then it's a dimension bound. And it's the same for 2-dimensional surfaces in higher codimensions. So Chang in 1988 again proved that the interior singular set is discrete. So in the first occurrence of singularity, in the first dimensional occurrence of singularity, we have a fantastic description of the singular set. It's a bunch of isolated points. And actually, we can say even more, even though I'm not getting to that point. So now there's one caveat with this result by Chang in 1988. It actually is based on the existence of an object which is called branch center manifold, which you should get after you read Andren's book, but not until the very end. You can stop a couple of 100 pages before the end. This was actually, I mean, it's a non-trivial thing to actually, prove the existence of this branch center manifold. And this has been done in a paper by myself, Spadaro, and Lucas Polaor in 2017. It's a quite long proof. Now, modulo this, then you can start actually with Chang's proof and prove the theorem. Now, in the case of hypersurfaces, in the 19th, there was a remarkable work by Leon Simon. So this is not Simons, this is Simon. And he proved that if you have an hypersurface of dimension m, your interior singular set is m minus 7 rectifiable. So now what is this m minus 7 rectifiable? It stays, I mean, if it were in 0 dimension, this rectifiability would just mean that the set is countable rather than being discrete, okay? So it's some sort of substitute, of measure theoretic substitute in higher dimension for countability in the case of 0 dimension. Well, here's the precise definition. You can cover your set with countably many C1 submanifolds of the correct dimension, okay? So not finitely many, but countably many. You would really like to state it that way, but there's a little detail that maybe, or you are allowed to leave out a set of m minus 7 dimensional Hausdorff measure 0. Okay, so up to a null set, you just have C1 surfaces, but they can be arranged in a very strange way, and they're just covering your set, right? I mean, your set can still be pretty bad. Okay, now, here's a typo. So, in 3 joint works with Paul Minter and Anna Skorobogatova, we just proved, and we are not in 2013, we are in 2023. So, this should be really 2023. So, we just proved the counterpart of Leon's theorem, in general, dimension and codimension. So take a general minimizer of the oriented plateau problem in the Federer and Fleming theory. The singular set, the interior singular set, has dimension m minus 2, but I'm telling you it has this rectifiability property. And this is a problem which has been open since actually Almgren's monograph, and it's kind of one of the hardest problems in geometric measure theory. We could solve it with 3 works, and remarkably, 2 other people discovered also a proof of this theorem, essentially at the same time, and also in 3 works. That's life. Anyway, there are several ideas which are in common, which we independently discovered. We were working at this at the same time. It's actually pretty lucky that, you know, we posted the papers we did a couple of days. There are many ideas in common, but there are also quite a few differences. So there is some stuff that we're doing differently and some other stuff that they're doing differently, okay? So now, I will give you an idea of what our proof is. I will not comment on how it touches with, you know, that proof also because, you know, it's a pretty cumbersome project in both, like, you know, implementations, and, you know, to tell you the truth, it's not I read every page of the other papers, and neither I think actually Brian and Eshan read all the details of our paper. But I think we start understanding what are, like, you know, the common points and what are the differences in discussions among us. Okay, now, before we actually get to an idea of the proof, you could say, like, okay, man, I mean, this rectifiability is kind of lame, right? I mean, maybe the singular set of this guy, I don't know, in dimension 3 is a bunch of curves which, I don't know, maybe intersect at one point. And, you know, you're telling me rectifiable. Yeah, but rectifiable, you know, inside the curve that covers your set, maybe there's an ugly fractal which is sitting there. So the information is not that much. Well, it actually turns out that you can't expect much more than rectifiability. It's almost sharp. So there is this theorem by Liu in 2021. So he's a student in Princeton. Actually, it tells you, take the case of higher codimension, fix a dimension for your surface, and fix any number which is below the allowed dimension of the singular set. There's an example of a smooth Riemannian manifold, really C infinity, of an area minimizer of dimension m, which has a singular set of fractal dimension alpha. So there's a 3-dimensional area minimizing integral current in the sense of Federer sitting, in this case, I think, in a 7-dimensional manifold, if I remember the dimensions correctly, which has a fractal singular set of dimension pi divided by 4. Okay? There's a similar theorem by Leon Simon for hypersurfaces with a very different construction, but it doesn't quite get to area minimizing. It gets to a stable minimal hypersurface. So, you know, for people who know more, it's kind of almost a minimizer. You could imagine maybe it's a local minimizer, although I don't think his construction is strictly stable. But, okay, don't quote me on that. Okay, so you are almost optimal. Except maybe instead of proving that, you know, there's a countable cover, maybe you can prove that kind of the volume is finite, okay? The m minus 2-dimensional volume is finite. So that's correct for hypersurfaces through a deep theorem by Neighbor and Valtorta, which was published 6 years ago, I believe. But it's still open for both of our groups. We don't know how to actually show that the set has finite volume for the corresponding dimension, which would be m minus 2. And it seems like a very, very hard refining of our ideas. I mean, it seems we're pretty far, both groups. Okay, so now in the last 15 minutes, let me give you some ideas about the proof, but let me first start with some ideas in regularity theory. So there's a first step in the regularity theory of area minimizers, or of minimal surfaces in general, which is called monotonicity formula. It's a beautiful discovery. It's the following discovery. So if you have a minimal surface, this ratio, so the mass ratio of what you find in a ball, divided by the corresponding scaling for the radius, or if you want, divided by the corresponding m-dimensional volume of a flat disk, this quantity is monotone, non-decreasing in R. Well, with a caveat. Of course, your ball doesn't have to intersect the boundary of sigma, okay? It's an interior thing. Now, why is this actually beautiful? Not only the computation comes with the fact that this guy is monotone, it has a formula, which is pretty explicit. And the formula also tells you that if instead of being monotone, this function is constant, then your surface has to be a cone. And why would you be excited from passing from a general surface of dimension m to a cone of dimension m? Well, because a cone has one direction, which is trivial, and so what really actually matters is the cross-section, which is an m-1 dimensional surface. And so you've kind of, if you can achieve this kind of conical condition, you've simplified the geometry of your surface, and you're trying to understand something which is simpler. For instance, if you were trying to analyze two-dimensional surfaces, but instead of analyzing two-dimensional minimizing surfaces, I tell you to analyze two-dimensional minimizing cones, then you're really discussing curves in the end, because you're really discussing the link of the cone, okay? Well, now, this is a corollary. So take a point P and zoom into it. So apply an homotopy to the surface. Applying homotopy keeps actually the area minimality condition invariant. Now take a sequence of scales which is going to 0 and keep zooming. You have compactness in your space, even if it's a pretty shitty space. And so it gets to a limit. And the limit is going to be a cone because of this monotonicity formula. So let me give you an illustration. But before giving an illustration, let me tell you one open question, which is maybe what is considered the biggest open question in all of this stuff. In principle, the limit that you find can depend on the chosen sequence. And it's a very big open question to understand whether the limit is unique. It depends only on the point, but not on the sequence of rescalings. Or if you might have, for area minimizers or for minima surfaces, a kind of crazy oscillatory behavior around the point between different singularity models, which would be kind of nightmarish. So there are fantastic results in certain situations, but the general problem is very open. Okay, so here's what is happening, right? So you have your surface, which is depicted by this line. I fix a point x, and I fix a scale r. And what I'm doing is I'm rescaling this disk or this ball to unit 1, right? So this is the image of the rescaling. Now, of course, if I am in a picture like this, in which I'm applying a homotopy at a point inside a smooth surface, when I let the radius go to 0, I converge to a unique limit, and the unique limit is a plane, possibly with multiplicity. Okay? So the object that we see is what in the language of geometric measure theory is called the tangent cone. And so you know that if you are at a smooth point, there is a unique tangent cone which is planar, where at most you can pick some integer multiplicity for it. So now there's a very interesting question, which can you ask the reverse? So does the existence of a single planar tangent cone at a point P actually guarantees its uniqueness, first? And then you're going to ask even a more kind of daring question. Can you actually characterize smooth points simply by the fact that in first approximation you see, in some weak sense, a planar tangent, right? So because the convergence is not a smooth convergence a priori, it's a convergence in a very bad topology. Okay, so we leave this question aside. We will see some answers. But first, let me get to the so-called Federer's reduction argument. So in 1970, Federer observes the following. So if you have a cone S, you can consider the set of directions along which it is translation invariant. Okay? And that is what he calls a spine. And he has a beautiful lemma. So the spine of an area minimizing cone is a linear subspace. So you can always study the structure of the cones by first studying a linear subspace of translation invariances. And then you have a core, which is a cone with no invariances. Okay? So it has a tip, but it's not invariant under some lines. Okay, now it has another observation. So take 2 points P and Q, which have a certain distance. And I'm telling you, in these points P and Q, which have distance r, I'm drawing 2 balls, and I'm telling you, in this ball, you're close to a cone, and in this ball, you're close to a cone too. So, and there's a zone in which the 2 cones have to have some compatibility. In that zone, the spines of C1 and C2 must actually align. They cannot be very transversal. They can only be a little bit transversal. And a little bit because I'm telling you, you're close to the cone, but you're not exactly the cone. But if you were exactly the cone, then you would have a rigidity. Now, you can use this to bound the Hausdorff dimension of the singular set when the answer to the question that I gave you is positive. So when the existence of a planar tangent cone guarantees you smoothness. This is his observation to bound the Hausdorff dimension of the singular set in the case of hypersurfaces, okay? So here is a picture, right? So you have these spines of the cones, which kind of align this way, and somehow if you're looking at a cone with maximal dimension for the spine, which would be m minus 7, an outcome of the codimension 1 regularity theory is that the singularities have to be clustered close to the spine for your current. And then, you know, if these guys, they're not varying too much, you can actually efficiently cover with balls. That's his idea. And it's called Federer's reduction argument. Now, in a tiny portion of his monograph, actually, Almgren generalizes Federer's idea. And so Federer proves in the hypersurface case there is at least one tangent plane at each point P, with the exception of an m-7 dimensional set, okay? Almgren actually proves in general that you can stratify singular points according to the maximum k of the dimensions of the spines of the tangent cones. What you would really like to do if you had uniqueness is just would like to say, well, give me a point P. If there is a unique tangent cone, tell me what is the translation invariant dimension, the maximal translation invariant dimension. So that is a number k. Okay, then I call that the k stratum. So ideally, if that k is equal to 0, I find scattered isolated points. But if that k is equal to 1, I find maybe a one-dimensional stratum, okay? And in fact, that's what he proves. So the strata has Hausdorff dimension k. Now I have to take the maximum k among the dimensions of the spines of tangent cones because I have this problem that maybe the tangent cone is not unique. So it's a technical point, if you will. Now there are two notable corollaries. So first of all, in general, higher codimension, you know that there is at least one tangent plane outside of a set of dimension m-2. That's why you hope in higher codimension to bound the singular set with this magic number m-2. So everywhere else you have at least one flat tangent cone. But you can study the m-2 stratum, and on the m-2 stratum, so there is an m-3 dimensional subset, which is exceptional when you see like lower dimensional invariance. On the stratum, which is top stratum, if you want, when you don't see any tangent plane, actually the cones of maximal invariance, which is m-2, they all look like planes which have a common m-2 dimensional linear subspace as an intersection. So you kind of see a very nice object. So if you were a three-dimensional current, you see three-dimensional planes which all have a common line, okay? Very well. So now, why is codimension 1 a much easier theory than the higher codimension, where Almgren has to suffer that much? So that's because there is something which is called the Giorgi epsilon regularity theorem. So the Giorgi proved the following. So the answer to that question which I posed you, can you characterize smooth points by the existence of a flat tangent cone, is yes. If you have a point and you see at that point a flat tangent cone, your surface is actually smooth there. But the Giorgi comes with a better information. So if at some scale, say at scale 1, you're epsilon close to a flat tangent cone, for a sufficiently smooth epsilon, which depends on the dimension and maybe the volume of the cone, then you're smooth in the ball of radius 1/2. So at the first scale in which you get sufficiently close to a plane, you'd know smoothness at half the scale, which is a very powerful theorem to have. Now, a scaled version of this, of course, can be easily reached by applying homotheties, and the reason why in higher codimension things are much more difficult is that the statement is false. So here is an example. This z squared equal epsilon w to the power 3. It's a holomorphic curve, and if I take epsilon very small, this holomorphic curve is almost indistinguishable from two copies of a plane. It's very, 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 very close. But it's always non-smooth at the point 0. And the Giorgi's theorem in codimension 1 tells you that doesn't happen, okay? So what is actually Almgren doing in his 1980 monograph? Well, I could summarize it in the following fact. So, okay, in higher codimension, when the current is sufficiently close to a plane, you cannot say that you're smooth, but you can find a best smooth approximation that is what you call the center manifold, and a finer harmonic multi-sheeted approximation on the normal bundle of the center manifold, okay? And there's one crucial information. This multi-sheeted expansion is non-trivial. So this multi-sheeted expansion could actually coincide, could be all the sheets coinciding with your smooth part. So this one is non-trivial if and only if the current does not coincide with the center manifold. So either this guy is non-trivial or the point is a singular point. So Almgren's theory was reworked and simplified by myself and Emanuele Spadaro between 2009 and 2016, and that spurred a lot of activity in the area. But let me give you an illustrative example of what I'm saying here. So here, this W squared would be the best smooth approximation, so the center manifold. And then you see there's a finer approximation which would be given by the square root of W to the power 2023, okay? So that's what you're capturing with the second expansion. It looks like some sort of, Taylor expansion if you want. So the only caveat is that if you do it in that way, of course, I wouldn't be on the normal bundle, so it's kind of slightly tilted, the approximation of Almgren, okay? So that is what I'm going to call Almgren's expansion. And what is the first idea of the proof of rectifiability? Well, first of all is to use this powerful result by Neighbor and Valtorta and just to say, well, the K-strata of Almgren are actually K-rectifiable. So there are no m-1 dimensional stratum because there's no cone which is invariant under only m-1 dimensional linear subspace. And the n-dimensional stratum consists of points with at least one tangent cone. So those points are either regular points or are flat singularities. And so the only thing I'm left with is to prove that flat singularities are m-2 rectifiable. And now, if you have a subset of your flat singularities over which the Almgren's expansions vary nicely, so that is the second idea of the proof. For instance, if the regular parts, which are approximating at each point, can be patched into a coherent manifold, then actually I can prove that S is m-2 rectifiable. And it's not I, actually this is a joint work with Anna Skorobogatova, one of the papers that I mentioned, and it's based on the previous work by myself, Marchese, Spadaro, and Valtorta. In a sense, we were kind of in an idealized situation in 2018, and we've been able to kind of carry it over to the full problem. So now, there's another idea. So this needed coherence of the approximations of the expansions holds actually on the subset of flat singularities at which I have these two informations. So first of all, the flat tangent plane is unique. And second, there is a power law decay to it. So if I have these two informations, I can start actually patching them together in a nice way. So now here comes the third idea of the proof of rectifiability. So this is another paper joined with Anna. So you can actually define the Almgren's expansion, and you can say the following. At each flat singular point, and at every sufficiently flat scale, the multi-valued approximation is radially homogeneous. So you have a smooth expansion, and then you have this multi-sheeted approximation, which is almost radially homogeneous. Moreover, the homogeneity, which we call singularity degree, depends only on the point and not on the scale at which you are. It's always the same homogeneity, even though the approximation might be different. The homogeneity is at least one. This uses ideas of Simon and Vikramasekera. And most importantly, if it is larger than 1, or it is larger than 1, if and only if we have a power law decay to a unique tangent cone. So we can attach a number to the set of bad points where we cannot coherently patch all the smooth approximations. So now here's what we then conjectured after these two works, which are ready since almost a year. So maybe the bad flat singular points where I cannot actually patch because the singularity degree is 1 is a null set. Then I'm done with rectifiability, right? So because I have the rectifiability of all the rest. And that's what we prove in the paper with Paul Minter. So the conjecture is correct. And moreover, as a byproduct of our proof, the tangent cone is unique m-2 almost everywhere. Okay, so that's our main theorem, and the proof involves combining Almgren's theory with Simon's techniques on the analysis of tangent cones, which were developed by Leon in the 90s. This borrows very important ideas from a paper by Vikramasekera in 2013. And another crucial ingredient is proving a L2 infinity height estimate. And I'm seeing I'm out of time, so I wanted to actually give you this estimate, but let me cut it over here, so I told you a lot. Thank you for your attention.
Thank you, Camilo. I'm supposed to say that there's no time for questions, but I will not do that. So let's allow ourselves some more time for asking questions to our speaker, please. Don't be shy.
Hello, so thank you for this wonderful talk. I have one doubt. So these spines of the cones, okay, so I am trying to imagine geometrically, but I cannot imagine more than 3 dimensions. So is there a characterization of cones that have like non-trivial spines?
Yes. So, I mean, in the following sense. So your cone is going to be a product of this subspace times another cone that has no invariances. And so it's sort of like, okay, think about, for instance, the Simon's cone and multiply it by a line. And then you have an 8-dimensional cone, which is area minimizing. So the spine is just going to be this line you multiplied by, and then kind of the core, which, you can't, it doesn't have any translation invariant, is going to be your sort of building block for the singularity. Of course, it's very difficult to analyze what are the possible singular cones which have no translation invariance. I mean, that's a kind of huge open problem, even in codimension 1. For instance, in codimension 1, it's known, there are product of spheres, not only S3 times S3, there are other products of spheres, and you can understand which product of spheres have a cone, which is area minimizing, but that's about it. And it's not known if there are other cones, as far as I understand, in codimension 1. In higher codimension, there's a huge zoo of area minimizing cones. I mean, there's the beautiful theory by Harvey and Lawson of calibrated geometries with which you actually produce a plethora of examples but then you are sort of on the other side of the spectrum. I mean, there's so many that looks almost daunting to try to classify them.
Well, I'm going to ask you maybe a strange question, but I'm wondering if this nice theory has some possible extension to area minimizing currents with constraints. So, as far as I understood, all your theory is in free space somehow. But if you, the analog and again dimensions to the obstacle problem, you take the minimal surface with obstacle. Now, are there any theory for area minimizing currents with obstacles? I mean, the set, now to be sets.
Yeah, I don't know about that, actually. I mean, probably you can do something in codimension 1, but I don't think there's anything in higher codimension. I would imagine there's something in codimension 1. Yeah, but I wouldn't be able to actually cite literature right now. I mean, these objects in codimension 1 have the maximum principle anyway, so some form of the maximum principle, which would help you in that situation. There's a form of the maximum principle also in higher codimension, but then you would have to compare the surface with something which is still an hypersurface somehow. Then you can't pass through. But it's a less powerful tool. So I would imagine it's a much harder problem in higher codimension. Right, but probably in codimension 1 it does exist because you can actually characterize your area minimizing currents as boundary of sets. And so from the point of view of existence theory, I don't think there's any problem. Then probably there's also works on regularity, I would imagine.
Camilo, Where does the number 7 in the regularity theorem come from? Is there a philosophical reason for that?
So it's a tricky question. So first of all, this cone was actually found by Simons in his paper in which he was showing that there are no, so that all hypercones which are area minimizing, they have to be planar up to dimension 6. Okay? So, and that's actually what sort of, started this improvement in the regularity theory. Right? So, I mean, the Georgi has the absolute regularity theorem, and then has, I think, either he or Fleming, I don't remember, has the observation that, two-dimensional area minimizing surfaces in R3, which are cones, have to be flat. And then so two-dimensional surfaces are regular. And then it gets upgraded. And Almgren upgrades up to a certain dimension. And then Simons found the optimal upgrade, meaning that, so these computations only use the stability of the cone. So then in dimension 7, so he's using something which is called the Simons inequality. And I mean, like, among the computations, there's a coefficient which changes sign at 7. And so then he cooked up this example, which is a stable. And then Bobieri and the Georgi and Giusti proved it's an actual area minimizer. But, okay, so you go down, you compute, you see this m minus 7 coming out, but it's just a purely algebraic computation. So do you have an explanation of why actually that thing happens at 7? So, I mean, one hand-waving explanation which tells you what might happen somehow in higher dimension is that because of the scaling, like, the volume of, say, half the ball is much, much smaller than the volume of, like, 1 unit ball, right? And sort of like, constructing this cone seems to be more and more energy efficient, mass efficient if you go higher up in the dimension. That's some sort of hand-wavy explanation of why you might expect something bad when you go higher up at the dimension. But why 7? I don't think anybody has an intuitive explanation of what happens at 7.
Do we have more questions? Okay, then why don't we thank Camilo again for this very nice.